Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Today's guest is Stuart Kauffman, one of the foundational figures in complexity science.
Great to be here. It's wonderful to be told I'm a foundational figure in complexity science.
True. It is true enough.
It makes an old man feel good, whether it's true or not, Jim.
It's true, at least in my opinion. Stuart was trained as a medical doctor, but is best known for his work in developmental genetics, evolutionary theory, theoretical biology, and especially the emergence of order in far from equilibrium complex systems. He was one of the first generation of resident faculty at the Santa Fe Institute. He has won a number of awards, including a MacArthur Fellow, and is the author of several interesting and important books. His most recent book is A World Beyond Physics, The Emergence and Evolution of Life, which we're going to talk about today. But before we do, I'd like to recommend two other of Stuart's books. His Origins of Order holds a special place for me. It's the second book in the area of complexity science that I read, checking my Amazon account way back in 1998. It's both thick and dense, but it's amazingly rich in ideas, and I still use a lot of those ideas today. It's one of the most important books I've ever read, to tell you the truth. The other one I'd like to recommend to our folks at home is At Home in the Universe, which serves as both a good layman's introduction to complexity science, as well as explaining many, though not all, the ideas from Origins of Order in a less dense form.
I thought that was great, Jim. And, I get about a penny and a quarter when the book sells. So I'm retired now, and, it could become a source of income. They're actually good books. Origins of Order is really thick and dense. It's about 700 pages. It took me 10 years to write. I'm glad I was younger.
I actually love that book, but that's just me. But before we get started talking about the specifics of your new book, maybe you can start off with some thoughts on the overarching themes of your career. What's your career been about?
That's an interesting question. Everybody's intrigued if they're asked a question like that. What my career has been about, in a funny sense, has been finding interesting questions. One of the important aspects of science is finding an interesting question. People don't talk about it, and you can't get a grant for it. Who's going to give you a grant to say, I'm trying to think of a question? But I've done that a number of times. When I was about 25, it had been discovered that genes turn one another on and off by Jacob and Monod in 1960, which answered central problems in evolutionary and developmental biology. And I wondered, were there classes of networks of genes turning one another on and off that had spontaneous order? And to ask that, I invented random Boolean nets, and lots of interesting stuff followed. They can exhibit order. They can be chaotic order or critical, and it's turning out the genetic nets are critical. A few years later, I was wondering about the origin of life, and everybody knew about template replicating DNA and RNA, and I asked a funny question. I said, well, what if the constants of nature were different, and you couldn't make nitrogen and carbon, but you could make chemicals? Would life be impossible? And my thought was, that just can't be true. Life has to be a set of molecules that can mutually catalyze one another's formation. So I came up with the idea of collectively auto-catalytic sets. And roughly 50 years later, literally, 48, it looks like that's right. Joanna Xavier and Bill Martin in Dusseldorf have found a collectively auto-catalytic set of small molecule metabolites in archaea and bacteria from before oxygen was in the atmosphere, strongly suggesting that life started as molecular reproducible systems. You might want to talk about it. It's fascinating. So I keep finding these wacky things to think about. And some of it's now standard complexity. The Santa Fe Institute in my early life, I guess it was in my 40s and 50s, not that early, was just an amazing adventure. And I've gone off in other directions thinking about quantum mechanics and the mind-body problem and how to answer Descartes 350 years later. So it's just a sprawling mess.
But isn't it great you could do that, right? I probably have had a similar model that, though at a less grand level, I've been in lots of different businesses and organizations and projects. I'm one not to let too much grass grow under my feet, though I haven't had a chance to address some of these grand problems. Let's hop in and talk about A World Beyond Physics a little bit. One theme that comes up again and again in the book is the notion that Darwinian evolution is incomplete with respect to the origins and evolution of life. Could you expand on that?
Well, Darwin knew that. That's nothing new. Darwin takes on the evolution of life once it has started, but he's silent on the question of how life comes to be. So that's not me saying that. Darwin himself said it. He said there's sort of no point on speculating about that at the present time in 1859 or 1860. He does say, but what if there were a warm little pond with ammonia and other things? What would happen? So many of us are thinking about what happens in warm little ponds, and we're the ones who are concerned with the origin of life. Darwin would have completely agreed. It's not an insult to Darwin at all.
Though don't you also talk about the fact that at least the biological implementation of evolution has other things going on, significant other things going on other than Darwinian evolution, other ways in which order is formed?
Well, yes. My first book, my tome, Origins of Order, takes up the theme that, and I don't think Darwin would have minded this at all. I think he'd have been delighted. There's a lot of self-organization out there in which things spontaneously get organized. And, why wouldn't natural selection make use of that? So that's what my whole first book's about. And that looks like it's true in lots of cases. So I could talk about that for a minute. The biggest thing about the new book is it says the evolution of life can't be explained by physics alone. So we should really talk about that. But just briefly about self-organization. So to get your listeners on board, just think of a snowflake. It's got six-fold symmetry and beautiful snowflake structure. And nobody thinks natural selection did that. There's a spontaneous order, and it's due to the space group of relevant oxygen and a couple hydrogens that make up the water molecule. Or think of a quartz crystal. It's got beautiful structure. Now think of a whirlpool. Whirlpool's got structure. They're called dissipative structures. So there's structure around all over the place. If you take lipids and put them in water, like cholesterol, they form hollow vesicles called liposomes that are essentially the origin of your cell membranes. Well, it didn't take selection to do that. That's physical chemistry. What I was struck by was, on the one hand, my study of these random Boolean nets as models of genetic regulatory networks. Jim, they just have astounding order. When I first found it, as I said 50 years ago, well, I was 25. I'm 80 as of a couple of weeks ago. It knocked my socks off, and it still does. But that's a case of self-organization, not in the sense that there's a self, it's just a spontaneous order that appears at the level of a system of simple components. Here, there are just a bunch of light bulbs hooked to one another, turning one another on and off. And all you have to do is make networks with 1,000 light bulbs turning one another on and off. And each light bulb has inputs from two other light bulbs and is guided by some rule, like called a Boolean function, like or and, where or says, I will be on if either one or both of my inputs are on, and and says, no, both of my inputs have to be on. So for two inputs, there's 16 Boolean functions, like if and nor and so on. Just make a random network with 1,000 light bulbs, everybody having inputs from two light bulbs, and give each light bulb a random Boolean function like or if. Those networks turn out to be with just stunning order, which I ran across and was thrilled about when I was 25. And why wouldn't evolution make use of that? And it does. Those networks are dynamically critical. And literally 50 years later, maybe in the last couple of years, we now have good evidence that genetic regulatory networks are critical. They're critical means they're dynamically critical. They're poised, in doing Farmer's lovely phrase, on the edge of chaos. They're between order and chaos.
Yes, that was one of the big takeaways out of Origins of Orders, the whole idea of criticality.
Much credit to Chris Langton, who did much to discover it and hasn't been able to pursue it for other reasons.
Why don't we take a little aside here, because this is something I know our audience is interested in, is this idea that's oversimplification, but fruitful things happen at the boundary between order and chaos.
Well, they do. There's something else I want to talk about, Jim, as we get along. I wrote down an equation about 2 years ago that is utterly relevant to us now, and it's not in my last book. But let's just talk about fruitful things on the boundary between order and chaos. So an example is your brain is dynamically critical, And as I said, genetic networks are dynamically critical. What happens in such networks is that just imagine a bunch of Christmas tree light bulbs twinkling on and off in some pattern. And you can ask the following question. If you change a given light bulb right now from on to off, just transiently flip it, call it damaged, color it purple. And now watch, if any other light bulb, that's connected to it, 1, 2, 3 steps away, does something different than it would have done, color it purple. So that's called damage by Dietrich Stauffer. And so you get avalanches of purple guys. And what Dietrich and others have found is you get a lot of little avalanches and very few big ones. So a bit of mathematics. If you plot this on a log plot, we all learned logs, in the 10th grade. So 10 is 10 raised to the first power, 100 is 10 raised to the second power, 1,000's 10 raised to the third power. It's just the number of zeros. So if you make a log plot of these avalanches, it's a straight line down to the right, and the steepness of the thing is minus 1.5. That's called dynamically critical. So critical networks do that, and part of what it means is one variable can sometimes influence things nearby, but sometimes things far away. So it's got a pretty wide span of control. Deep in the order regime, if you trigger a light bulb, nothing much happens. And if it's in a chaotic regime, if you flip one light bulb, roughly half the guys change what they're doing. You get these vast avalanches. And that may be why it's really good being on this edge of chaos. Or another thing is a fancy word called transfer entropy. And it's roughly how much do the variables now control what happens in the future. And that's maximized in critical networks. So let's see if we can think of some other examples. I think there's work that I know a little bit about. My wife, Catherine, does. I believe that this is true. If you think about birds flocking, birds try to stay some reasonable distance from the other birds. They try to head more or less in the right direction. And I think that bird flocks are dynamically critical. I think ant nests are dynamically critical. I'm not sure about this, Jim, but it seems to be a general feature.
Interesting. And, we have human artifacts like the electrical grid, which is known to be on the edge of chaos. If you had made it too ordered, it'd be too expensive. If you made it too chaotic, it wouldn't be very useful.
Right.
In fact, some Santa Fe Institute folks have worked with people at Aragon National Labs and essentially proven that the electrical grid is inherently unstable and does indeed have failures on a power law distribution, which would lead us to believe that it's somewhere in the critical range.
Right, and that's this interesting work that's grown up. When I did my first work, 50 years ago, I made what are called Erdos-Renyi Networks. It just means you got a bunch of light bulbs and you randomly connect everybody. And all I could think about is a random wiring diagram, Erdos-Renyi, or a regular lattice, like you put everybody on the corners of a tile and connect them to their nearest neighbor in 2 dimensions. And I knew that this is stupid. There was something in between it, like everything, but I didn't know what to do. Well, Barabasi and others, and Mark Newman have developed, and others have developed a whole thing called network science, in which you have some nodes that have lots of things that are connected to. They're called hubs, and others that are connected to not too many things. And that's power law distributed. And a lot of people study that because they're resistant to damage. If you knock out the rare hubs, you damage a lot. But if you knock out guys that aren't connected to much, you don't damage very much. And there's a whole literature about that.
Indeed. And of course, we're finding in the social sciences, social systems, that at least roughly power law distributions are turning up all over the place. A lot of dispute on how close they actually are to power law distributions, but they do have that attribute: deaths and wars, size of traffic jams, size of companies, size of cities that have this similar kind of distribution. It seems to be a regularity that appears again and again in complex systems.
Does. By the way, there's a wonderful book by Jeffrey West called Scale that your readers might enjoy.
In fact, we'll be having Jeffrey on here, I think, in November.
Good. But look, I want to talk to you about, if I may, about this equation that I wrote down.
Let's do it.
Because, Jim, I think I've stumbled across something that is much more important than I realized when I wrote it down. So I'm not much of a mathematician. Literally, here's what happened. My wife, Kate, and Jim Harriet, a friend, and I were up at my summer home on a little island near Seattle called Crane. And I wondered about the following thing. Suppose I know there's M goods in an economy at time t. So M sub t, like M is 24 goods in the economy now. Could I write down some equation for how many goods would be in the economy at the next time at M of T plus 1? And I thought something really simple. M of T plus 1 will be what we've got now, M of T, plus, and here's the central idea, Jim, plus all the new things we can make out of the 24 things we've got lying around now. So I could take any one of the 24 things and see if I can do something interesting with it, or I could take any pair of things and try to make something out of it, or any triple of things and try to make something out of it, and so on. So to give an example, the Gutenberg printing press is a recombination or a combination between a wine press and movable type. The Wright brother airplane is a combination between an airfoil, a light gas engine, bicycle wheels, and a propeller. So I just wrote down literally the simplest equation you can write down. It just says, you got the M things you got now, and you got some chance of making something useful out of all the single things, some smaller chance of making something out of all of the pairs of things, but there's a lot more pairs of things than there are single things, right? And an even smaller probability of making something useful out of triplets of the 24 things, but there's an awful lot of those. And this equation does something amazing. Apparently it hadn't been written down. There's now theorems about it that Mike Steele has produced. There's 2 papers on archive, but nothing published yet. Here's what it does, Jim. So put time on the horizontal axis and M, the number of goods, on the vertical axis. This thing goes along and increases very, very, very slowly, glacially for a long time. Then all of a sudden, it skyrockets upward in a hockey stick. And most importantly, it goes to infinity at some finite time. It goes vertical. It's called a pole mathematically. So that was interesting. And I got in touch with a friend named Roger Koppel. You might want to talk to Roger about it. He's at the University of Syracuse, an economist. And Roger looked at it and he said, that looks like the Industrial Revolution. So we worked with this equation, which we call T.A.P. Boldly, it's the theory of the adjacent possible. And it turns out, I'm finding this remarkable. So let's pause over it, because it actually has societal import. 2 million years ago, our ancestor Australopithecus, 3 million years ago, started making stone tools. And they had maybe 10 really crude tools, like unifacial stone scrapers. Over a couple million years, not much happens. And we get to Homo erectus and Homo habilis. Homo sapiens is around 300,000 years ago. Some Homo sapien bones were just found in Greece from 210,000 years ago. Not much happens. You get to Cro-Magnon, who's us, 30,000 years ago. They now have a few hundred tools, ranging in complexity from arrowheads to, do you know what the atlatl is? It's really neat.
Yep.
Yeah,
Spear thrower.
Yeah, they invented the spear thrower. So that's a really complex thing, and it helped a lot. You could throw your spear at the auroch, from 15 feet away rather than running up to it and jabbing it, particularly if it was something, bigger than an auroch. So they had a few hundred tools ranging in complexity from simple things to more complex things. Part of what I want to convey is how long everything took. It took 100,000 years to get to Cro-Magnon. That's human. That's us. That's humans, ignoring Neanderthal. It takes another 10,000 years to get to agriculture. When agriculture comes, we get to Mesopotamia 5,000 years ago, 4,000 years ago, on the Tigris and Euphrates. They had a few thousand kinds of things, ranging from needles that have been around for 60,000 years to chariots. So see an increasing diversity of things and an increasing diversification into simple and more complex things. All of this falls out from this little T.A.P equation. Well, then you get to us now, and this process skyrockets upward. We now have billions of goods, ranging from needles to space stations. Jim, nobody knows how that happened. I think this ridiculously simple equation says it, but it says more. What it says is that the more things you got, the easier it is to make yet more things out of what you got. And we are now zooming upward almost vertically. That's why we're in the Anthropocene. Now, we're the same species. We can invent things so trivially now. We have a $100 trillion global economy growing at 4% a year, inventing ever more new things, lifting millions of people out of poverty, and invading every niche on the planet. We're destroying the planet with our own creativity. And this simple little equation says it. So it's T.A.P. It's this process. Buried in it are a couple more things. You make the next more complex thing that you make out of the less complex things you got now. You couldn't make a space station, till we had rockets. You couldn't make a crossbow till you had a bow. And this little process reinterpreted says the same thing. It says at any time t, the last thing you made is the most complex thing you got. The next thing you can make can be more complex. And therefore it gives rise to an increasing number of things, but increasing differentiation to simple and more complex things, okay? So Tim Kohler is an archaeologist who I'm now working with. Tim's looked at the onset of inequality in humans in Neolithic sites, in 67 Neolithic sites from 30 or 40,000 years ago. It's called the Gini index. There's already inequality way before agriculture. You find Neolithic sites with simple graves, and at the same place there's more complex graves. I was stunned to find that in one of them I read, there's 3 adolescents buried, and they have very complicated necklaces around their neck with shells from a couple hundred miles away. That tells you that 30,000 years ago, since they're adolescents, there's inheritance, there's a marked differentiation in wealth, and people are gathering shells from a couple thousand miles away, a couple hundred miles away. So you have the onsets of inheritance, inequality, and the same little equation says inequality. If you can make chariots and you can make needles, people who own chariots have more valuable property than people who have needles. So the same process gives rise to, or is part of giving rise to, inequality. And inequality is now one of the overwhelming things on the planet. Look at inequality in New York. It's the worst it's been in history.
Go to San Francisco and see 10,000 people living on the street in the richest city in the world, probably.
Somehow an awful lot of this is a consequence of the same simple process. But even more struck me, it's taking me some time. This is barely said, Jim. It's certainly not published. But think about the Big Bang. So here you have the Big Bang, and you got quarks and gluons and stuff. And the 3 quarks get together. It's called hadronization. It's roughly the same process. All this T.A.P. process does is it says, take what's lying around and make new things out of it. Doesn't have to be a person. So what happens in the early universe is you get quarks and antiquarks, and they combine to make protons and neutrons and electrons, which combine to make hydrogen and helium. Then 3 helium nuclei get together to make carbon. So what happens is 2 heliums get together and they make beryllium. So watch, 2 things have gotten together to make a new thing. Then beryllium and helium combine to make carbon. So now you've got the synthesis, nucleosynthesis in the stars of 100 nuclei that are stable. Then you start getting space chemistry. So you've got the atoms of organic molecule, carbon, hydrogen, nitrogen, and so on, and you start making molecules of increasing complexity. It's roughly the same process. New things get made out of old things, and it doesn't matter whether it's pots or ideas or molecules. It's the same wacky process in which you take things and combine them. And I'm starting to think the following. I think if one looks at the chemical evolution of the universe, it probably looks like T.A.P. It goes along very, very slowly for a long time, then it starts shooting upward. And some evidence for that is that meteorites, the Murchison from 5 billion years ago, has 35,000 organic molecules. So does the Enceladus, the moon of Saturn. If you go through its jets, have thousands of organic molecules. And a guy in Germany, Albrecht Ott, has just done an experiment. It's worth pausing over this. Do you know the Miller-Urey experiment?
Oh, yes, where the lightning in the bottle and the
ammonia.
So
Miller and Urey did this in the 50s. So they took a flask, they have water in it, and carbon dioxide and methane and ammonia, I guess. They were trying to mimic the atmosphere of the early Earth. And they sent electric sparks through it, trying to mimic the early atmosphere. And Miller was a young graduate student, and Murray was a Nobel laureate in chemistry. And 3 days later, or 4 days later, they had a brown scum on the bottom of the pot. They looked at it, it was full of amino acids of different kinds, and everybody was rightly excited. It said, gosh, look at this. We can have the synthesis out of simple things of the building blocks of life. And that started a 40-year search to say what else you could make that way on Earth. And then we learned there's infalls of meteorites that brought stuff too, like the Murchison. Well, roughly in the last 2 years, this guy, Albrecht Ott, OTT, who is at a university in Germany, I can't remember what, he's done the following amazing experiment, Jim. He's taken the Miller-Urey experiment, and I guess he's let it run for a month. He gets thousands of organic molecules. I'm calling it a spray. Well, I think he's getting what the universe has done for the past 13 billion years. Molecules make more molecules, which can combine to make more molecules, to get more complex. And I'm wondering whether or not there's a hockey stick evolution, gradual for a long time, then scooting upward really fast as the universe makes more complex molecules. So, for example, this means that 5 billion years ago, if the Earth had a soup of 35,000 or so organic molecules, so did planets everywhere in the universe. Out of which, by the way, you could have gotten life because they could have been self-reproducing molecular sets. So this TAP thing may be catching something really general. It looks like it's capturing something about technological evolution, about cultural evolution, about the evolution of the chemistry of the universe. It's so simple. You just take what you got and combine it and see what new you can make out of it.
You do have to have a pruning rule, which is that many, in fact, most combinations make no sense, right? Have no utility. Right. And the generativeness of the pre-existing set is highly dependent upon the rule of which combinations make sense and which ones don't. And it's certainly possible to have a transition matrix in which the result is only minimal increase in complexity over time.
Yeah, so let's hold right there. So let's get to economics, which is what you're talking about right now. I'm not sure that applies to molecules. I don't know. I mean, there's going to be some stability for different molecules. One way of asking it is to take this Albrecht Ott system and say, what does this look like over time? I don't know that Albrecht's looked at it. One could look at it. In fact, a group of us is trying to get money from CERN to look at just that. So now let's take the economy. So you're right. So my old example is I take a parachute and I put it over the stack of the Queen Mary, and you just get a mess. But if you put it at the back of an airplane and it pops up when the airplane lands, you made an air brake. So only some combinations will produce something useful for a given task. I mean, maybe you want to put it over the smokestack of the Queen Mary for some stupid task. Only some combinations will prove useful, and that's actually already in this little equation. It says, out of all the possible subsets of 3 things out of 1,000, which is something like 1,000 times 1,000 times 1,000, which is, I guess, 1 billion, only a modestly small subset will be useful for any particular thing. So one of the ways I think about this is like jury rigging. Would you rather jury rig with a garage full of junk or almost nothing? Well, you'd rather jury rig with a garage full of things, because if you got a bunch of stuff out there, I said technically, you'll find something to jury rig to do lots of different things. That's real technical talk, but it's true. Jury rigging is not algorithmic. We just go do it.
And indeed, it certainly speaks to both common sense and basic quantitative analysis that the more components you have to try, the more likely you are to find something that actually does make sense.
Right. But the thing that I'd like us to just pause over, Jim, we really are in the Anthropocene. We are living in a 100 trillion global economy. It really is growing at 4% a year. It really is lifting millions of people out of poverty, in China, for example, right now. And it really is invading every niche on the planet. Did you see the UN report about extinction events?
Oh, yes.
That came out a couple of months ago?
Yep. That
it's expected by 2050, 20% of all species is going to be extinct, 1 million species. What are we doing to the biosphere? We're eradicating it. You can recover from global warming, which is a catastrophe, in thousands of years. Recovery from a mass extinction event is millions of years. We have no idea what we're doing and what it doesn't parallel. I don't even know how to say it, Jim. What can you imagine that will slow down this juggernaut of an expanding economy, inventing ever new things, doing ever more huge projects, decimating the globe?
And certainly we're getting close to the edge. I mean, 2 of my favorite scary statistics are the mass of humans and their domestic animals, mostly cattle in terms of actual weight, is now something like 60% of all large mammals on Earth. That's absurd, right? And for birds, the number's even higher. The weight of all birds in the world is utterly dominated by domestic fowl under the control of. Yes, I couldn't believe it when I read that. So I researched it and found it referenced in multiple places.
Jim, it's terrifying. Something really struck me. We debate whether or not humans are having an impact on the globe. So just think of this. So 35,000 years ago, there's Cro-Magnon, and they're living in the caves of the Dordogne in the north of France, in Spain. And they're there for 15,000 years, and they paint the walls of the caves. And they go from, a few hundred kinds of tools to a few hundred kinds of tools. And then some of them migrate north when the ice sheets go away, and the guys in the north of Spain, I guess, stay there and go clam fishing or whatever. For 10,000 years or 15,000 years, they're there. They're the same species, and nothing much changes. Two things. My father was born in 1903. I'm getting at the rate of change. And it's buried into the fact that the more stuff you got, the more stuff you can make in the same period of time, right? So my dad was born in 1903. My son was born in 1969. My dad was born the year flight was invented. My son was born 66 years later when we landed on the moon. The pace of change is enormous because we can make so many things so fast. Now for the impact on the planet. So I'm 80, gosh. So I was born in 1939. I grew up with milk being delivered in milk bottles. In The Graduate, Dustin Hoffman is famously told, think plastics. Well, plastics was a big thing in 1960. 60 years later, 2020, we have crashed our oceans and our seashores all around the planet with gargantuan piles of plastic crap that will not decay in thousands of years. And we're making more of it. Have we affected the planet in 60 years? Well, there's masses of plastics floating in the oceans, and we didn't even have plastic 60 years ago. So let's not debate the fact that humanity is impacting the planet. We're overwhelming it. And we're not being mean. Nobody's mean-spirited. It's not capitalism. It is the inventiveness of the T.A.P process in which we inevitably invent more things that are useful for stuff, and we just keep doing it.
If it's inevitable, and the T.A.P equation at least says the adjacent possible will exponentially increase over time, how do we get out of that? Is there any way to get out of it, or we are going to just go up against the limits and crash? T.A.P, if it's fundamental, would indicate that might be what happens.
Jim, it's worse than exponential. An exponential never reaches infinity in finite time. This thing goes vertical. It reaches infinity in finite time. I think we are now going steeply up this curve, and this is the Anthropocene. And what we confront, one could say this, and it's so stark. What we're confronting is global, and what we're confronting is civilizational. This is our own humanity creating, and we're wonderful at it. We've been doing it for 3 million years. Overwhelming the planet. This image came to me a couple of weeks ago. Easter Island. Mm-hmm. So there's Easter Island, and the stone figures facing east. It's an island out in the middle of the ocean. What did the person who cut down the last tree think? Well, the Earth is an island in space. Jim, we're cutting down the last tree. We have to find a way of becoming aware of this as a species. With all of our interscene identity politics and Muslims versus Jews versus Hindus versus whatever, and the civilizational goods and bads of a global civilization emerging, and if conceivable, make some transformation in which we find valuable human lives when we are of nature, not above it. Western society, there's this amazing line by Francis Bacon, in about 1660, the West is just turning to look at the real world. This is the start of empirical science. And Bacon says, I take all knowledge to be my province, which was easier then, there wasn't as much. Then he roughly says, doesn't quite say this, but it's his meaning, to put nature on the rack and rest our due. Well, that's the center of extractive modernity.
And it works within the context of the rules of modernity. The problem is we've now reached the limits, and our social operating system seems to have no way to constrain itself.
That's right. It's overwhelming, Jim. I'm living in a beautiful house in Santa Fe with Kate, and it's got all the conveniences. And as Jeffrey West says, enough energy per person to be 1,000 slaves, and we're already comfortable. We have, as a species, a planetary species, essentially to become aware of the implications of this T.A.P thing that I wrote down 2 years ago. That's why it's happening. It's not malintent. We're no different in our intent than people were 40,000 years ago. Not much happened for thousands of years with the same emotional structure then as now. It's just that we can create so much out of what we've created that we keep creating. We're going to die by our own creativity.
As we were talking about earlier before we went on the air, there's something charming about life in America in the 18th century. And the energy density was vastly lower. We would not be destroying the planet if we had somehow found a way to say stop, right?
But what happened in 1840 was we were on the frontier of the Industrial Revolution, and we've exploded since then. And per capita GDP has gone up faster than population growth can. So population, for the first time in history, it started exploding a couple of centuries ago, and there's 7 billion people now because per capita GDP is going up faster than population.
Yep, and you multiply the two together, and you're, at least at a rough order, the load on the ecosystem. And as we were just saying, we've got to be getting close to the limits. And the operating system itself has no means to correct itself, or at least it's very, very difficult. In my own work in politics, I analyze the engine of money-on-money return. It's now become unleashed from human control. Everybody dances to money. And money corrupts politics. And until we learn to develop a new social signaling network or constrain the power of money, it's not obvious to me how we can stop this beast driving us right over the cliff.
I think you're right. It's driving us over two cliffs. It's certainly that the rich get richer, the top 1%, the top 10th of a percent. Have you seen Thomas Piketty's discussion of this?
Yeah. I've read Capital, and I've read some of his more recent articles.
So I've only read about Capital, but I think I understand it. His basic idea with respect to this is a tax that just taxes people on big estates. Take any estate over 50 million and take away 2% of it every year and put it into a general pot. Well, that would do it. It'll never pass, but that would do it. In a sense, Elizabeth Warren's doing that or proposing that. But Jim, that won't do anything about the fact that we're inventing ever new things and processes and ways to make bubble gum and purple plastic penguins for the poolside and apps and new kinds of penicillin and new kinds of gadgets and new kinds of vast projects like the Silk Road that the Chinese are doing now that is just going to keep invading the planet. Even if we were to distribute the money better and help inequality, what's going to slow down the juggernaut that's growing?
Yep, and here's the part that a lot of people have not caught, which is not only do we have this T.A.P.-driven, faster than exponential wave of new products, most of which we don't need or want probably, but the money-on-money return machine drives the psychologically informed marketing to invent new needs for you, right?
Well, yes, but pause. There's the inventing of new needs. Since who was the guy, Bernet, who was the nephew of Freud and my son, he invented in about 1920 advertising, and cigarettes are freedom candles or something. But it's more endogenous to that, Jim. Now, if you invent a screw, it needs its complement, the screwdriver, to be useful. So goods in the economy call forth the invention of still more new goods that are the complements or substitutes of existing goods. So once you got cell phones, you get apps. Well, once you've got rockets, you get the space station. Advertising is a piece of it, but this has been going on since long before advertising.
It's true enough. In fact, you made a big point of that in your book, that complementarity by itself draws forth the future, right? Especially in the economy.
By the way, it's time to mention Brian Arthur. Brian's book, The Nature of Technology, 2009, talks about lots of this. Brian, we're old friends. Brian doesn't have this equation, but he's got lots of the central tenets in his. You should really read the book.
Not only did I read the book, I actually read some of the chapters before it was published and gave him some feedback on it.
Oh, great.
Brian and I were actually office mates when I was full-time at the Institute back in 2002 to 2004.
Oh, really?
Yeah, so yes, I'm very familiar with that book. That's a must-read for anybody that's thinking in these areas. That book got less attention than it should have. It really
I
annoys
agree.
me. I mean, that is one of the most profound books on network models of one important part of the economy, which is the evolution of technologically driven products and businesses.
I think I agree with you. Brian set the foundation. And the stuff I'm talking about that grows out of it. There's now a bunch of us. And, Brian's doing it too. Brian even gets to the idea. Well, I did too, I guess in 1998. Brian and I were friends at the early institute. We kept going to Babe's for lunch. It was really cute because we'd go to Babe's and Brian would order fish stew. And each time he'd say, this fish stew is just terrible. And he'd keep ordering fish stew. It's really cute. Anyway, Brian taught me some economics and I wrote a paper in 1988 about it. Actually, I wanted Brian to be a co-author, but for some reason he didn't want to be, or it didn't happen. So once you start thinking about things making things, it's growing on how simple it is. Suppose that you have a number of things n, and in general, two things can get together and make a new thing, okay, like what we're talking about. Then the differential equation for the number of things is dn dt is equal to n times n, or n squared. Even I can integrate it. That means that, and I've checked it with Ricard Soleil. So if you integrate dn dt is equal to kn squared, if you integrate it, it is n is equal to n to the third per time, and that's hyperbolic. It goes infinite.
Times 2, yeah, but yeah.
Once you've got a general process that takes pairs of things and makes new things out of it, and you can sample pretty much the things that are around now, there's a process that looks like it's going to reach infinity in finite time.
Although I'll point out again, the fecundity filter makes it go not that fast, because not all the combinations work. In fact, the combinations that work are quite sparse, and if they're sparse enough, it changes from a hyperbolic to a parabolic, or even to a superlinear.
There's actual theorems that Mike Steele has produced in a paper that we've got online. This process is hyperbolic, but the model doesn't have the things die. Right.
Or things fail, or combinations fail.
Yeah. So if you put into the things just go away, so things can just drop out at any moment. So call that mu. Then if mu is 0, it goes to infinity. A theorem, if mu is a little greater than 0, it either goes to infinity or it goes to 0 at finite time with some probability. So we know a little bit about that. That's still not adequate because things don't die alone. When one thing dies, a bunch of other things die with it, and Schumpeterian gales have created destruction, and we don't know very much about that yet.
Well, this has been amazingly interesting back and forth about all kinds of cool things, but we've gone a long way from your book. One of the cores of your book is I took it away as the point of your book, was origin of life. Why don't we talk about what you think about the origin of life today, after having studied it for these many years?
It's so fascinating, Jim. Let me tell you how it's interesting how the problem arose. Before about the middle 1900s, there was no problem about the origin of life. If you looked at a rotten log after a rain, there were maggots. So they obviously had sprung forth from the rotten log. Wim Hordek, who's just written a review of the early of the origin, I'll send it to you. Finds this wonderful thing in which there's some doctor in 1740 who says that if you take a piece of cloth that is laden with sweat from your armpit and you mix it with wheat and you put it in a box, a mouse will emerge. This is my doubt. Okay. So what happened is that somewhere in the late 1900s or mid 1900s, there was a prize set by the French. People now had microscopes and they were making wine and so on. They found that if you put a broth out, a couple of days later, it was all milky and it was full of bacteria. And the question was this spontaneous life? So Pasteur did a brilliant, simple experiment. He made a flask, and the neck is S-shaped. It comes up, then down, then up. And he filled the neck where it's down with water. So air couldn't get in from the outside air to the sterile flask. And 10 days later, there was no bacteria in it. So after a very fine dinner of foie gras and bœuf bourguignon, people wrote differently. He says, life only comes from life. Well, that's right. But then the question comes, so where did life come from? So Pasteur sets the problem of the origin of life in 1870 or whatever. Basically, nothing happened around 1920. And Haldane and Oparin in Russia, and Haldane start to think about it. But Oparin says there's going to be coacervates, sort of little gelatin-like things in the early Earth. And somehow they're going to have complex chemical mixtures and life's going to happen. And Haldane comes up with the idea of a primitive soup in which there's kinds of organic molecules in the ocean. So for many years, Origin of Life talks often had somebody with some Campbell's soup can labeled primitive soup. Then Miller and Urey come along in the 50s, and they show, you really can make amino acids out of just the atmosphere. And Origin of Life sort of exploded then. And for around 20 or 30 years, even now, people are showing that out of beginning things, you can make things like sugars and nucleotides and lipids and so on. People don't know yet about this guy, Albert Och's result with the spray. I don't know why it's not getting more attention. It's amazing. So you wait for a month and you get thousands of organic molecules. So then what happened in the Origin of Life field is by 1954, we knew about DNA replication because Watson and Crick. So when I was coming into biology around 63 or 64, the obvious view about the origin of life was DNA is a double helix. It specifies its own sequence. So is RNA. You can make a double helix of RNA. And everybody had the idea, take a single strand of RNA, AUCG, some long polymer, call it the Watson strand. Will it please line up free nucleotides that will make this bind to the Watson strand? So you've got a bunch of free nucleotides, and then something links them together, and now you've got the Crick strand, which is its complement. They melt apart and cycle. And that's how life started. And that's a perfectly reasonable idea. It's a fine idea. Leslie Orgel and others have tried to do it for 50 years. The experiment doesn't work. It should, but it doesn't. And the reasons are sort of chemical. If the replicated strand is full of G's, not C's, it folds up in little knots and precipitates. And DNA and RNA have 3', 5' phosphodiester bonds, but thermodynamically they'd rather do 2', 5'. The quick summary is, all the years later, nobody's made it work. So pause. It's still the dominant view. And it became even more dominant in, I guess, 1986. The ribozymes had been discovered. These are RNA molecules that catalyze reactions. And Wally Gilbert published an article in Nature saying we can conceive of a world just with RNA molecules. Let's call it the RNA world. And that view has dominated. And what has dominated in that view of life is template replicating RNA. And it might work someday, and people are trying to make it work. Wim Hordak, I'll send you he's just written an article that came out in Biological Theory literally today. So Wim has traced the history of this theory of auto-catalytic sets, which actually I started and published in 1971. That idea is that I catalyze the formation of you out of 2 Jim parts, and you catalyze the formation of Bill out of 2 Bill parts, and Bill catalyzes the formation of Stu out of Stu parts. It's a mutually autocatalytic set. Nobody catalyzes his own formation. So there's been a lot of work started by me, I guess, in 1971. Then in 1986 with some theorems, and some work done with Don Farmer and Norm Packard, that you really can get these systems. Fundamentally, if you get a complicated enough system, it'll spontaneously make autocatalytic sets. So that was theory for some time. Then real ones were made. So Gunter von Katarowski made the first autocatalytic set out of DNA in 94. In about 95, Reza Ghadiri at Scripps made the first self-reproducing protein. He took a protein sequence length 32 amino acids that's an alpha helix that coils back on itself, making coiled coil. And he reasoned, as they say after the fact, that if he took the 2 fragments, 15 and 17 long, 2 fragments would bind to the 30-tumor and glue together, and he'd get the 30-tumor to reproduce itself. Well, it does. Within a few years, Gonan Ashkenazi, now in the Ben Gurion, had made a 9-peptide collectively autocatalytic set. Pause. That tells you that molecular reproduction absolutely does not depend on template replicating DNA or RNA. It just doesn't. So that happened experimentally. Then I told you that I think about 2012, Niall Suleiman and Vaidya published an article in Nature, I think was at that time the most important experiment on the origin of life. They took some ribozymes and chopped them in half, where ribozyme A chopped in half glue together with one of the halves of B chopped in half, and they put it in a pot, and it spontaneously made collectively autocatalytic sets of ribozymes. So that was superb, except so one get the spontaneous formation of collectively autocatalytic sets, and a bunch of us are writing about that now, but they're still using evolved molecules. So what we want to know is if you take random polymers, can you make autocatalytic sets? There's hints that you can. It's possible the fellow named Lee Cronin is doing that, but I'm not at liberty to tell you the details. He hasn't published it yet. We have this money I told you about to try to do it from CERN. And I told you the next most important thing that's happened is Joanna Xavier and Bill Martin, in a paper still not published, Mike Steele, Wim Hordick are on the paper. I'm a co-author, but I did nothing much on the paper except they put my name on it, and I thank them. They have found this metabolic autocatalytic set where no polymers in it at all. So it's almost sure now that life started in a rich soup of organic molecules everywhere in the universe around 5 billion years ago. What's missing, Jim, is how hard is it to get an autocatalytic set in a bunch of small molecules? And totally unpublished, Mike Steele is just proving theorems right now that it should be pretty easy. And if so, we might be able to detect it pretty soon experimentally. So I've got significant dreams that we can do that. The group of us that's got money from CERN is meeting soon, and maybe we'll think it's plausible to carry it out. And suppose that works. So you got molecular reproduction 5 billion years ago all over the universe, because the universe has cooked up this stuff. Well, so now you got this metabolic autocatalytic set. You'd like to get some polymers going. How would you glue the two together so you had the polymers catalyzing the reactions of the metabolism? How do you put the thing in a liposome that I told you about? Roberto Serra has shown that they will synchronize the division of the molecular system and the autocatalytic and the polymer system. So can we actually make protocells in the reasonably near future? Well, maybe. People always say it's around the corner, then it's not. So maybe we can. That's huge if we can do it. It's one of the great mysteries in science. How does life emerge? Maybe it's sort of a process of T.A.P and autocatalysis, maybe.
Let me push back just a little bit. I've been following this for many, many years, spent time talking to Norm Packard. I spent time talking to you back when I was at SFI. The one part of it that I have a hard time getting my head around and over is that these earlier prebiotic chemical regimes are not by any means high fidelity replicators. And right. we know from mathematically in evolutionary theory, there's something called the error catastrophe, that if the fidelity of copying is not greater than X, and X is actually a pretty crisp number for any well-defined system, the ability to ratchet evolution is surprisingly small. Entropy quickly breaks down what evolution builds up. And these are all low fidelity replicators. And yet our world, the world of all life that we know, is built on a high fidelity replicator. It's DNA plus replication plus error correction, which appears, at least empirically, to be well past the error catastrophe stage. So how in the world does this pre-life protocell chemistry world ratchet itself up with worse than error catastrophe driven evolution to create high fidelity information transfer? And if we can't do that, we don't actually get life as we know it.
The short answer is you're right, Jim. So here's sort of what we know. What I've told you does not get us to RNA template replication or DNA template replication or coding, encoded protein synthesis, where the deep mystery is proteins that are encoded are the amino acid synthetases that translate the code. There's some chicken and egg problem that's huge. How did that ever emerge? And we don't know. Peter Wills is working on it. A lot of people have worked on it for a long time. It's not cracked yet. There's some ideas. So I and David Deemer and others can fiddle around and have little protocells floating around without any DNA or RNA. Or you can put DNA and RNA. You can make an autocatalytic set out of RNA. Niels Lehmann did years ago. The question is, how do you get to something like template replicating DNA and RNA? And actually, Paul Davies rightly points out in his book on the origin, I've called the Demon in the Machine, the ribosome plus the code is, in von Neumann's sense, a universal constructor. It can make any protein out of the standard 20 amino acids. That's amazing. And just imagine what it left for the origin of life when that happened. You could explore protein space trivially just by making proteins. So there's some ideas about how the code could have emerged. I even have some ideas about how the codes have emerged. And I'm not competent to talk about it. You should talk to Peter Wills. Okay. It is clear that these auto-catalytic systems can evolve without encoded protein synthesis. And the reason is due basically to Mike Steele and Wim Hordick. I'll send you the link that they just sent me, that Wim just sent me. His article came out today. An auto-catalytic set is made up of a large number of irreducible auto-catalytic sets. And Strathmore led a group of us to show that these irreducible auto-catalytic sets could be gained and lost, the little replicating systems, and they're acting like genes. So you get heritable evolution from that. And as Doan Farmer and Rick Bagley showed years ago, you can imagine that uncatalyzed reactions happen. They can be captured by the system, and the system can evolve to some extent. Not like you can with encoded protein synthesis. Yep. So we've got it, and there's no talk of energy in all of this yet either. If you put things through a wet-dry cycle, it's called the plastine reaction. I was writing about it in 1993. Dave Deemer and Bruce Damer are focusing on it now. Dehydrating and rehydrating a liposome is adding energy to the system. And people are finding, Dave Deemer's got some wonderful things about the onset of transport across membranes. He's in Santa Cruz. He's really worth talking to. It's not there yet, Jim, but it's not as far away as it was.
Interesting. One of the topics we talk about a lot on this show is the Fermi Paradox. Where are they, right? And, called the Stuart Kauffman view, life's probably ubiquitous, right?
There's 10 to the 22 stars in the universe. It's now estimated that something like half of them have whole solar systems. So that's 10 to the 22 solar systems. Suppose 1 in 1,000 of them have life. So that's 10 to the 19th biospheres out there. That's a lot of biospheres.
If it turns out that true life is easily reachable across this information gap, this error catastrophe gap. And, when I was a 14-year-old nerd, I would have bet any sum of money that I had, which wasn't much, that there was lots of intelligent species out there. But the more I've thought about it, the more I've read on the Fermi Paradox and the various pruning rules, it's possible we might be the only one, right? If it turns out this gap is unbelievably hard and low probability.
Unbelievably hard and low probability, you're right. But if by my crude calculation, there's 10 to the 20th biospheres out there, then for there to be none, it's going to have to be really small compared to 10 to the 20th.
To make that clear, 10 to the 20 prebiotic, autocatalytic, metabolistic networks.
Just waiting for something like DNA.
Yes, this is where I've come out, is that Stuart Kauffman is correct, that probably there is an unbelievably large number of integrated autocatalytic and metabolic networks.
Inside of liposomes and budding.
Yeah, and inside of, fat buds, all that. Question is, what percentage of them ratchet up to having high fidelity information transfer?
Until we have some understanding about how hard it is to get to template replicating DNA or RNA or some other molecule that can carry, we're really talking about Schrodinger's what is life, an aperiodic solid, of which DNA and RNA are the wonderful examples, that can carry, as he says, a microcode for the organism, which DNA does. Until we know how that happens and the microcode is reliably transferred, we don't know. But it can't be that far away, Jim.
We'll find out as people are working on it. I still remain agnostic, right? But I will say I now give fair credit to those who say that leap may be so damn hard it only happened once. If that is true, this talk we had earlier about to destroy our ecosystem is even more, it's even more morally, it's morally loaded, right? If we're the only life in the universe, and one could say perhaps our destiny is to bring the universe to life, if we snuff out intelligent life, it'll not be good.
Well, I think some bacteria will survive.
Yeah, I think they will too, and probably even other animals, but will they get back to intelligence?
Cockroaches will make it.
Cockroaches we always have with us. Thank you, Stuart. This has been great. We've had a few technical difficulties. The audio is not going to be as good as it usually is, but man, what a great conversation, and that's the important thing.
I'm glad to have the opportunity. We all have to think about what T.A.P means for the Anthropocene and what we're going to do as a species. Everything else is trivial, Jim.
Yeah, it's interesting, the idea of T.A.P, because you actually express T.A.P without the equation in your book, right? You talked about this combinatoric unfolding of both life and economy. But once you have the equation, it actually is more stark and in our face that unless we figure out how to stop T.A.P, we're going to just run outside all the borders of every resource and crush our planet probably in the next 100 years.
I think that's roughly right, Jim. We are chopping down the last tree.
Yeah, that is an unpleasant thought.
What has to start happening, Jim, is we as a species have to take on what this means. And that is sober beyond anything we can say.
Fortunately, there's some people working on that. Some of the people I've interviewed on the show and will be interviewing on the show. What does the operating system of the future look like that has the attributes of allowing us to have an interesting, intellectually probing species, yet not destroy our planet? I will say nobody has solved that equation yet, but there are people working on it.
I want to hear more from you about it, Jim. Thank you. I'm hoarse.
Bye-bye. Take care. Be good. Production services and audio editing by Jared Janes Consulting, LLC. Music by Tom Muller at modernspacemusic.com.